Okay, good morning, and thanks to the organizer for the opportunity to come back home and talk about some recent work that I've been doing together with Franz, Sven, Andreas, and Andrea Pelloni in the direction of getting N3LO evolution in the parton distribution functions. And there are some works that are already out, and hopefully more in the future. Oh, shit. Yes. Okay, so here the challenge is really to get percent level phenomenology at the LHC. So we do expect, of course, that in the high luminosity phase, both systematics and statistics will just go down to the percent level errors, here in blue and green, and theory will dominate in many situations. And here there is a kind of recent breakdown of theoretical uncertainties that show you that, for instance, for Higgs measurements and N3LO, N3LO QCD correction are absolutely relevant. So the shift when you add the N3LO is of the order of a few percent, and so you would like to take that into account. And scale variations in many cases are reduced in the percent level, but in all this number in this study, you have always to add some extra error because these calculations have not been done with N3LO PDF. So to assess the size of this error, you just go one loop back, you go to next reading order, and take the difference between the full next reading order calculation and the next reading order where you use only the partonic part, two loops, and next reading order PDF. And this is how they got these numbers that they need to add. So the message is, if we want to get rid of them, we need N3LO PDFs. And to do this, of course, we need to compute the N3LO evolution. So the PDF, of course, evolve with Altair-Diglap splitting functions that mix quark densities with gluon densities, and for this reason, it's convenient to break them down into flavor non-singlet contributions, which cannot mix with the gluon, and singlet ones. And then you need to compute perturbatively the kernel. And if you want to get to N3LO, you need a for-loop calculation of these kernels. So recently, there have been lots of progress, of course, in this direction. First, in the large NF limit, where in 2016, there was an improvement of the original result from 20 years before. And then already 6 years ago, we had the complete planar limit of the flavor non-singlet evolution and an approximation of the complete QCD flavor non-singlet. And then we had to wait a few years to get the first 4 Melli moments of the splitting function that has already been used to get some approximate N3LO PDF. And this avenue of getting approximate N3LO fits is still ongoing. So, and now recently, since basically a few weeks, we have even the complete subleading NF, so NF squared contribution for the quark-to-quark splitting. In this talk, I was focused on a framework to compute Melli moments of this PDF that was used by us to get the first 10 moments of the quark-to-quark and gluon-to-quark splitting functions. And then I will comment a little bit about what can you do with these 10 moments. So the starting point, so why do we like Melli moments of the splitting function, is because the Melli moments of the PDF are just related to expectation values of local operators within the proton state. So where we can take a proton of a momentum p and evaluate just this expectation value. The operators are leading twist operator, so these are gauge invariant objects that you can make with field strengths and covariant derivatives. Then you need to project on the leading spin, so the maximal spin. You can do this either by symmetrizing and taking away the trace, or by projecting everything in a light-like direction, like here on the plus direction. And now, if you want to get the evolution, the scale of the evolution of the PDF, of course, this is connected to the scale evolution of the operators, so the renormalization of these operators that in general renormalize with a matrix of constants. That's the only object that depends on the scale. So when you compute the anomalous dimension by taking the derivative, one can see that such anomalous dimension are just, apart from a sign, the the Melling moments of the splitting functions that you need. So this is quite convenient because now in a minimal subtraction, you simply need, you can extract the physical quantity you want from the single pole of these renormalization constants. So just few diagrams to see why it is convenient. Let's start with the non-singlet case. You simply get to compute a two-point function with your operator insertions. You get your single pole, and from the single pole, you read off the anomalous dimension that you need. And of course, the two-point function are the easiest kind of integrals that can be done in quantum field theory. However, things are not so simple in the singlet sector because now singlet operator, as I said, can mix with each other. So you need a matrix structure. And if you repeat the same exercise, this is something that was done already a long time ago, you will find that your single pole have your physical contribution, your gluon splitting, but also some things that you don't want. And these were called back then kind of alien operators. And you really want to find out first what these operators are and what is the mixing with the aliens that you need to subtract. And this is especially true in multi-loop level. So what you want to do is just renormalize two-point function and extract the mixing constants. So diagrammatically, what happens is already if you go to two loops, you will get the diagram you had here as a sub-diagram of your calculation. So if you want even to get rid of your subdivergences, you need to subtract contribution from your alien and their mixing. Otherwise, you don't renormalize the objects. And of course, the one-loop case I showed before is not enough because you can easily find diagrams with internal ghost line that diverge. So you will need also some ghost vertices that I didn't show before. So the message is you really want to find your basis of operator and your mixing constants to extract the physical anomalous dimension. So this problem was first used attacked in Yang-Mills, again, long time ago, but only at two-loop level. So they wrote, these people wrote down a basis, Dixon and Taylor, for the alien that you need. So this is the structure in terms of field strengths and explicitly gluon fields. And these constants, eta and k, has to be computed or appropriately chosen to cancel the divergence. So this is really the mixing that you need to compute. And yeah, the first calculation can be found here, for instance, of these mixing constants that you need. The second piece of information that we have is a general theory on the renormalization of gauge invariant operators that says several things, but the take-home message is you need two sort of ingredients. So this operator that you need must contain the equation of motion, and you can kind of see the structure here. So if you integrate by part, you get the df here and the df here. So you can kind of think that Dixon and Taylor started to construct the operator by taking df and adding one extra gluon or two extra gluon fields with appropriate number of derivatives. And the second bit that you need are BRST exact operators, which is not visible here at first sight, of course. But I mean, we thought it was important to get across this point because we really, I mean, if you see at this basis, it's not easy to understand how to extend it beyond the two-loop level. So we said, okay, let's focus on this BRST property and try to find a handle to get the full contributions. So let's first review a little bit how BRST properties are in the normal Yang-Mills Lagrangian. So you start with your Lagrangian, which has just this gauge invariant bit. So it doesn't change if you replace your gluon with the covariant derivative of a scalar function. And then a second bit that is explicitly the BRST variation of what is called an ancestor operator. This variation is such that it operates on the gluon like a normal gauge transformation where you replace the scalar function with the ghost. And it's defined such that it's nilpotent. So in this case, it's transparent that the Lagrangian is invariant under BRST because the first bit, if you operate with S, will just behave like a gauge transformation and it's invariant. The second one, if you act again with S, you get S squared and is 0. So we said, okay, now we have to move on and generalize this picture. So we get we know that we must introduce equation of motion component that we decided to construct like Dixon and Taylor did. So we take the df and we add 1 extra gluon, 2 extra gluon, 3, and so on. Now we break gauge invariance because we have explicitly gluons in there. But what we found is that the first part is still symmetric under some generalized gauge transformation that I will show you later. Such a generalized gauge transformation will define a generalized BRST, so some S prime operator, and that will just generate for free all the ghost vertices that you need. So just to see how this works, as I said, you can, in general, write your equation of motion part as df times some polynomial. You are not gauge invariant anymore, but you will be obeying this rule. So the Lagrangian in the first bit is invariant under gauge transformation, plus these extra pieces that depend on the variation of this polynomial that you can write down. And then, if you promote this to a BRST, so if I just naively replace all this omega that I have in here and in these other 2 bits with the gauss field, I can see that this object is still nilpotent. So this S prime squared is still 0. So to have a look at the simplest case, how this can work, let's go to the first moment, n equal 2, where all operator must have dimension 4. Here I don't have much choice, so my only generic polynomial has to be just an A. Indeed, my equation of motion part can only be df times A, because I have to stay dimension 4. But then I can construct this extended generalized BRST, operate on the gauge fixing ancestor, and so the 2 extra bit of the transformation will generate a covariant derivative of the ghost, and a bit that cancels the interaction of the ghost. So I will just be left with a kinetic term. So I will have just one alien with one mixing coupling from the physical operator into the alien. And diagrammatically, the meaning is that I showed you before these diagrams. Well, okay, this is a subdivergence that will go like this vertex, like this df times A, and the mixing is some number eta that I can compute in principle from the 2-point gluon operator. This diagram will have a mixing into this kind of vertex, and the mixing will be exactly the same, and I can get this mixing by computing this 2-point subdivergence only. Of course, once you go with a higher dimension, the situation is more complicated because you can add more and more gluon fields, more and more derivatives. But this is basically how it works. The one thing that we have to add now, if you want to go to QCD, is to consider Quark operators and Quark fields. Now, but these are much simpler if you want. So already in this one loop example, you can see that the Quark at one loop cannot mix back into some alien. So if I just repeat this exercise to compute the gluon to Quark moments, I will just get my physical answer. And again, if you want, BRST can guide you, because you know that you have an alien whenever you can also have ghost diagrams. But if you have a Quark operator at one loop and a ghost diagram, you cannot construct anything. You need at least 2 loops. So once I do, I replace this bubble into a 2-loop case, I can see that the 2-loop renormalization doesn't need any alien in this case, only the physical one, and I will need alien only from 3 loops onwards. Of course, one caveat is that now the equation of motion will change, and you have to add this term in the operator that I showed before. So armed with this consideration, we started, of course, renormalizing Quark operators, which are simpler, and we don't need all the huge towers of operators as before, but just 2. The one with 1 extra gluon and one with 2 extra gluons. There are couplings, and we found some relations from BRST and another kind of symmetry that I'm not discussing here. And also what we found is that at the level that we need, so we need basically 2-loop mixing between the Quark operator into the aliens, these constants factorize and just are proportional to this eta coupling, which is the coefficient of the simplest case. So we can get it from 2-point function, and indeed this is what we did. We computed this mixing to 3 loops, and we found agreement with another group that used completely different methods. So this was okay. So after this alien part was under control, you can proceed and compute the full for-loop correlators. We used the code Forcer, which is already public since many years, and we got the first 10 moments up to n equal 20. The checks that we have done was to just check the first 4 that were already published, plus other 2 will appear soon. The important bit is that these moments were computed in a completely different method, which use only on-shell quantities, and once you are on-shell, you don't have any alien contamination, so this was a good check to make us sure that we were not messing alien in the procedure. The large NF limit was good with the result known, and since a couple of weeks, we could check that even the sub-leading terms are good for these 10 moments. So once you have this, a procedure that's following, for instance, this work on the non-singlet, that you can do is to construct some approximation, constructing a set of trial functions that reproduce your first 10 moments and known limits at low x and large x. There will be then some still divergent bits that you need to fit. So the first thing that you want to do is to make sure that you can reproduce the tree loop, so next leading order result with these approximations, and indeed you can. And then you can go on and produce here are 80 curves, and choose two extremal one as a confidence interval. There is, as you see, for large x, you have quite small errors, and they will always grow at low x. To kind of estimate how important is this error, you first construct the next Q-below correction by fixing alpha strong to some value and summing 1 loop, 2 loop, 3 loop up to 4. And again, you see that there is some spread at small x, so this is the error of the approximation. However, one always has to remember that in the physical quantities, you need to compute the convolution between the splitting function and the PDF. Now, so the splitting function at small x will be multiplied by the PDF at large x. And the PDF tend to fall quite badly at large x. So this is a model PDF that was used just to give some estimate. So what happens is that the error that was still visible here becomes just invisible after you convolute it in the physical applications. So to cut the story short, similar procedure we applied to quark gluon mixing. We got 10 moments and got agreement with first 5 moments in this case and the large NF limit. And you can construct an approximation. Here the important point is that here is a bit more tricky because there are still some coefficients at large x that are unknown and diverge. So if you compare the quark to quark case, the unknown coefficients were all suppressed by an extra power of 1 minus x in front, while here you really have some large unknown. So as a result of this, the error is larger at small x. Again, you construct everything, you construct the full approximation with fixing your value at 0.2, and you can still see kind of 10% order error in the approximation at low x, which again becomes much smaller after you convolute with the PDFs. So at this point, you can start constructing. You look at some physical application. You can start to see really what is the scale derivative of the singlet distribution. So you simply combine the quark-to-quark approximate evolution convoluted with the singlet and the gluon-to-quark convoluted with the quark. And one nice thing that you see is that the contribution of the next Q-below normalized to the next leading order is of the order of 1% up to 10 to the minus 4, and then grows a little bit, but is definitely much smaller than the next leading order, which was up to, if you go down here, around 10%. The only inconvenience is that, of course, the scale derivative vanishes around 0.1, so there is a pole, but this is just an artifact of the presentation. And then you can assess the impact of the renormalization scale variation. So you can change the renormalization scale that here was fixed as the factorization scale, and take the maximum minus the minimum, normalize with the average. So you can see once you go to this approximate N3LO, you always stay with scale uncertainty that are below 2% up to 10 to the minus 4, and get at most to 3, while you had basically 5, 6% before. So get to my conclusions. I wanted to show that it's quite convenient to compute moments of the splitting functions from just renormalization of 2-point correlators, provided, of course, you are careful with your aliens. We do find some BRST structure that fixes the contribution of these aliens, and we see a tower of contributions that we can become more and more involved, that we call class 1, class 2, etc., where here you add higher and higher point vertices. However, for instance, for the relation of the quark, you don't need all of this, and everything is quite treatable. So I presented the result for 10 moments of quark to quark and gluon to quark splitting, first 10 moments, and approximations of the X-space results. The message is we always get larger error at low X, and okay, the quark to quark is pretty well under control. The gluon to quark still has some 10% uncertainty, but this becomes very small after you convolute with the actual PDFs. The effect of the next N3LO correction on the scale evolution of the singlet is order of 1%, which is quite good, and we get always scale stability, which is much better than next to next reading order, going down below 2% compared to 5-6 that we had. Future work, of course, we are working on the gluon operators, so quark to gluon and gluon to gluon splitting. And one question that you can ask is, will you ever get exact results from this procedure? So one thing I didn't stress during my presentation is that we can reconstruct the selected coefficient of zeta numbers and selected color factors, and we write them in the papers, but of course these do not translate to the same coefficient in X space, because when you do the Mellin transform, you just generate other zeta values anyway. The main message is what is hitting us is that we have large error at low X. So if we were able to fix the next to next reading log at low X, which is a log X over X at 4 loops, all these fits will improve quite significantly, and hopefully even you will be even in the position to fit the exact result. But of course, first, I don't know this coefficient. I would like to get there, but and second, I don't know whether it's enough. In general, if you want systematic approaches to get the all end result you did, we are working also on different methods. So there are also other groups that are doing that. And thank you very much for your attention.
Thank you very much, Giulio, for this very nice presentation. Questions? I don't see any. You were extremely clear. No, perhaps Massimiliano. Okay.
So, very, naive question, but so I mean, how much will we have to wait until we get a solid N3LO fit? I mean, if I look at what was done by Robert Horn and his collaborators, it was first attempt, but there are a lot of assumptions, and this is not to me yet something which one can. I mean, it's nice to see that it's the first step, but so I'm wondering, so how much, what is the timeline? When can we expect a reasonable fit using your results?
Well, okay, I'm not doing the fit
yeah,
myself.
Sure, but, so, but you are adding more and more information, so.
Yeah, so if the question is when are you going to finish this, the gluon sector, I hope within 1 year to get that. but I'm always conservative, so keep that into account. We'll see. I hope 1 year from now we're getting something.
Okay. I have a question myself, which is related to the one that Massimiliano asked. So you say that basically we need the N3LO because of this uncertainty that you estimate. So if you want to get rid of this uncertainty, we better know the N3LO PDF. But what is the status? Because as far as I'm aware, there were previous studies that were claiming that to actually describe, I mean, the point is that if you want to reduce this uncertainty, that's fine. And until you don't have the N3LO PDF, you don't know how much is the shift. Mm-hmm. But what is the idea there? I mean, is it known that because there have been previous studies that claim that you don't actually need the N3LO PDF to have the description because the shift in the prediction is negligible, or could be considered negligible. Has this view changed over time? Because this study were a few years back.
So I guess depends who we ask.
Okay.
I mean, I think in general, I mean, if you want to be conservative, you don't have explicitly this N3LO PDF. You better add this 2%, even if you don't know better. Yeah, I think
because I mean, maybe I didn't follow the thing correctly, but I think this early estimate of the N3LO PDF, they were actually giving quite sizable shift if I have understood correctly.
So what we find here, like for the shift, I mean, just on the evolution is, yeah, you're right. What we see is that we get, so the next cube's shift compared to the next is percent. But I mean, you want to know that. Okay, a posteriori you can say, well, I could have forgotten about it. But yeah, I don't know.
So if you want that level of precision, you better have it. Okay, thanks. Sorry for.
I think Andreas.
It's just a curiosity. I'm always curious about the possibility of having mixed QCD, QED PDFs. Okay. And now the question is whether in this formalism you can also account for some subset of corrections which could be interpreted as a QED exchange.
I think so, yes. I mean, I think so. I haven't thought about that, but it should be.
There should be the possibility to identify.
I think there should be, but okay, yeah, I think so.
Okay, maybe.
Yeah, thank you for your nice presentation. I have one quick comment regarding the whether we should do the N3LO declub evolution. I think, I mean, this should be done as a matter of principle, I think, because it's inconsistent what we're doing right now, right? So, I mean, you need a reason to drop it, not the other way around, right? It's not that you just, truncate earlier in the expansion. So.
Posteriori.
For not doing it.
It's like leaving out the virtual corrections and so on, right? I mean, it's okay. Maybe you can do this as a first step, but
about the impact of physical distribution in the end.
Okay, so okay. But my actual question is whether what you have in mind regarding prospects to tackle the small X region separately, is this something you actually intend to do, or think is a reasonable approach? Or do you think one should skip that and do the all N result instead?
The thing is, so for other reason, I'm looking at the moment at next leading log reg things for others. So I mean, it's convenient for me to look at that as well. So I think I will have I want to study that. Cannot give timescales because I haven't actually started. But yeah, it's something that it's interesting per se. And can be useful also in this context. That's a message. Yeah, of course, the collaboration is larger, so there are also attacks at the end, at the more general methods as well. But.
Other questions? If not, let's thank Giulio again.
Thank you.
And we are off to the first lunch.